My name is Terrence Barkin, the Executive Director of the Graphene Council, and we're very pleased to host today's webinar on the use of graphene for EMI shielding, presented by Graphenest and led by Bruno Figueiredo, who is the CEO and founder of the company. So with that, Bruno, I'm going to just hand over to you and tell us about what you have to present today.
Okay, so thank you for the introduction, Terrence. Good afternoon, everyone. It's a pleasure to be here today. Like Terrence said, I'm currently the co-CEO of Graphenest, not the CEO. I'm a co-CEO of Graphenest, and I've been a graphene evangelist since 2014. So I founded Graphenest with my two co-partners, and since then we are trying to bring this material from the lab to the market. So for today, my goal for this presentation is to elucidate a little bit how Graphenest is overcoming the challenges of EMI shielding with graphene-based compounds. I hope you enjoyed it. So my presentation has the following content. I will begin with a brief overview of Graphenest. Then I will dive into the critical needs for effective shielding systems and what is the problem we are facing nowadays in this scope. After this, I will introduce our product portfolio and delve into the features and applications of our two flagship products, namely G-Shield and X-Shield. So who are we? Like I said, we are a company, a Portuguese pioneering company. We right now have 9 years of expertise. Currently, our dedicated team are composed by 9 people, and we operate pilot plants and 2 state-of-the-art laboratories. To date, we have secured 3.3 million in indirect investment and plus 1.3 million in grants. To date, we have also filed 7 patent applications concerning the production of our own graphene and the formulations of graphene-based compounds coatings. We are members of the Graphene Flagship, of the EIT Raw Materials, and members of Techstars as well, because they are one of our investors. Our business model focuses on collaborative product development, using our graphene production and expertise, and it is tailored for EMI shielding. But to be clear, we are a reliable producer of graphene, and we use our own graphene on the development of graphene-based shielding solutions for electronics and e-mobility. So here at these pictures, you can see our pilot plant on the warehouse and one of our labs. So in today's interconnected world, everything from smartphones to cars relies on seamless connectivity. So it doesn't have to be cars or neither smartphones. It can be home appliances, power tools, and so on. So this means that ubiquitous networks are transforming our world. But if you look at the car example, we can see how complex is the modern connectivity. For instance, we can look at different kind of connectivities like the 3G, 5G, LTE, for instance, vehicle to infrastructure, so the V2X that typically operates at 5.9 gigahertz, but also high frequency bands like the radar that operates at 77 gigahertz, which is the E-band, and beyond. So clearly, a panoply of different signals are emitted and or received by this vehicle. And this applies not only to cars, but to other products. So what's really the problem? Current metal-based shielding systems face several drawbacks, including weight, cost, environmental concerns, and susceptibility to corrosion. So metals are 10 times heavier than plastics. Their production cost raised more than 50% in average. They have high intensive process and large carbon footprint. They are highly reflective in high frequency telecom like the radar and lidar. So in this case, you want to avoid reflection, but we're going to get there in the next slides. And to finish what I was saying, metals are also prone to corrosion, which somehow may be a drawback for certain applications. So at Graphenest, we came out for now with two product lines, so G-Shield and ExaShield. G-Shield on the left can be found in different polymers. At the moment, we have polypropylene, which was co-developed with a British company named Ubron. And we also have PVC, which was co-developed with Delta Technique. But we have others coming shortly, namely PBT, PPS, PA6, and PBT. Sorry, I repeat myself. PAPS, PA6, and polycarbonate, sorry. In relation to ExaShield, we also have two versions available, one water-based and other solvent-based. And in this respect, more details will be given in the next slides. But the value proposition of these products is clear. These solutions offer great performance across a broad brand frequency range, while enabling lightweight, cost-effective designs. So you can customize them according to certain process and product requirements, and somehow reduce operational and fixed costs while using them. Okay. In the present slide, I would like to revive how to interpret shielding results. As you can see in the table, shielding effectiveness is typically measured in decibels, which is a dimension in the log scale. So if you take, by example, the image below, a wave is being propagated and has an incidence on a planar shield here, made of any material, so the material is not important at this point. And as you can see, part of the wave is reflected through the reflection mechanism, while the remaining penetrates the shield. While part of the penetrating wave is absorbed, again, through the absorption mechanism, a slight part is transmitted. So at the end, the best shielding material is the one that does not allow any part of the wave to be transmitted. So let's now take attention to, pay some attention to the table on the top. And for instance, take into consideration a shielding effectiveness of 30 decibels. A material with this level of shielding allows only 0.1% of a wave to be transmitted. So this means that 99.9% of the wave was attenuated, either by reflection or absorption mechanisms. So on the left side of the slide, you see the equipment that we use at Graphenest to measure the shielding effectiveness. And it's basically composed by a two-port network analyzer, a VNA, which is capable to perform measurements optimally up to 4.2 gigahertz. Of course, this depends on the waveguides. As you can see, we have at Graphenest, we have two waveguides, one with a frequency of cutoff of 3.2, and another one which was built with a cutoff frequency of 4.2 gigahertz. So these measurements at the end provide us with some parameters known as scattering parameters, which are the return loss and the insertion loss. And those parameters allow the precise characterization of shielding materials, including the reflection, absorption, and transmission properties. So let's now explore G-Shield, starting with our PVC-based solution. So on the left, we can observe the shielding spectrum. So in this case, the magnitudes in decibels versus frequency from 30 megahertz up to 3 gigahertz. And this sample is a 2 millimeter planar slab, which was prepared by extrusion. So here at the plot, you can see the role of reflection and the role of absorption. But don't be, please, misguided by the impression that reflection is smaller than absorption. And I'm going to explain why in a few minutes. So let's now take into account the table on the right, where we have the results of 3 different thicknesses. 1, 2, and 3 millimeters. As can be seen, changing the thickness does not change much the surface resistivity. So the surface resistivity is between or among 5 to 8 ohms per square. So less than 10 ohms per square. And that is why the reflection mechanism has an almost identical role in the 3 samples. So as you can see, in terms of decibels, it is 9 to 10 decibels of reflection. On the other hand, increasing the thickness is benefiting the absorption mechanism and the overall shielding. So at 1 millimeter thick, we have 27 decibels of total attenuation, while at 3 millimeter thick, we have 41 decibels of attenuation with this graphene-based PVC. So this is very well aligned with theory because shielding, the reflection mechanism of shielding is impacted by the surface conductivity of the sample, while the absorption suffers from the thickness of the sample. But we can discuss this theory in a following upshot after this webinar, if you have some interest. Despite the fact that our PVC G-Shield excels at the S-band, it also excels particularly at high frequencies like the E-band. Well, this band which is 60 to 90 gigahertz, is relevant for high-density wireless services, radar applications, and others. As you can see on the left side of the slide, we have a picture of the equipment that was used by a courtesy of a partner. But now let's take a look on the plot on the middle, when I'm plotting the insertion loss as function of the frequency again. So decibels as function of megahertz, gigahertz. And as you can see in the plot, the performance of the graphene-based PVC is exponentially enhanced, attaining an attenuation of 99.9999% at 77 gigahertz. But why so big difference? So let's have a look, or let's make the exercise on the right. So at the UHF S-band, only 12% of an incident power are allowed to penetrate the shield. So roughly 87% is reflected. While at the E-band, this value is roughly 32. So much less power is reflected at high frequencies. However, as you can see from that 32 that tries to penetrate the shield, only 0.0001, which is the 100 minus 99.9999%, is allowed to be transmitted through it. So at the end, at high frequencies, we have more shielding because we have less reflection and more absorption. Early adopters, such as power cable manufacturers, have seen remarkable results with our G-Shield solutions. After a long period of trials, it was possible to check that an hybrid configuration can be qualified for a power cable. So at this case, we decided to go with an hybrid cable which comprises 0.5 millimeters G shield and 55% braiding, which is the green plot. And this design, like I was saying, qualified, so more than 50 decibels, even at lower frequencies, so less than 450 megahertz. And actually, it equals conventional solutions in the S band, so 2 to 4 gigahertz. This innovative shielding solution, or this design, in this case, offered great benefits. In this case, substantial weight reduction up to 50%, cost savings, more than 20% reduction in production cost, basically because of OPEX, and more product output, increased product output up to 40% times, because in this case, the bottleneck is the braiding. So the power cables need braiding, and the bottleneck of production is the braiding process, which is very, very slow. Well, while our G-Shield PVC was very nice to have in power cables, the scenario in data cables is not as good as expected. So we have tried to produce a Cat6 data cable, substituting the metallic tape foil with our G-Shield. And in this case, the results were not the ones that we expected, because actually the material has a high absorption mechanism or high absorption feature. So mostly at high frequencies, so above 200 megahertz. So as you can see on the left down plot, the attenuation as function of the frequency. In this case, is the attenuation of the signal being carried by the cable. So dB per 100 meters. After 200 megahertz, we start to see that the signal is lost. So in this case, what is happening is that the G-Shield is exacerbating the attenuation of the signal because of its absorption mechanism or absorption feature. And the reason why can be also related to the dielectric constant of the material. So the permittivity is around 210 at 100 megahertz, which is a little bit high for this kind of applications. Right now, we are actively researching and developing solutions to address these challenges, but we don't know yet where we're going to end up. Looking ahead, there are two different things that we can explore for data cables. So first of all, is to check the opportunity at low frequency, but for this we need to maintain the electrical field and contain the electrical field within the cable core. But for this kind of application, maybe polar plastics might be not the right solution. We need to check, because at low frequencies, the dielectric constant is typically high, while at high frequencies, the dielectric constant is typically low. Maybe the best solution will be to use a non-polar plastic, because its dielectrical constant is independent of frequency. But we need to check. The other thing that we can do, or the second scenario, will be to change the cable design as well, like we did for the power cable. And we are proposing to produce an hybrid cable again. And in fact, we are on the verge to do it with a French company. And we're going to keep somehow the individual shielding of the pairs and substitute the collective shielding. So typically the aluminum foil around the shielded pairs with a graphene enhanced polymer. But this is something we are still looking on. Let's now look at G-Shield made of PP. Again, on the left, we can observe the shielding effectiveness as function of the frequency, depicting again the reflection and absorption mechanisms as function of the frequency. In this case, we are talking about a 2.7 millimeter planar slab, and instead of being extruded, it was injection molded. Our polypropylene G-Shield offers similar performance to PVC. However, as you can see, and if you can remember the last values, the reflection mechanism has a smaller role, so more absorption. Even so, this material promotes with this thickness 3.5 decibels of shielding, which is 99.97 of the wave, of the power of the wave being attenuated. Both G-Shield products were compared against commercial alternatives that use other conductive fillers and base materials. Namely, in this case, competitor one that has a commercial product with ABS and stainless steel fibers as conductive filler, as well as a thermoplastic elastomer that has carbon black as conductive filler. So the values from C1 were gathered by the TDS of the product, while the values from competitor 2 were measured here at Graphenest with the product in hand. To make a proper assessment, we decided to plot two figures of merit. The first one on blue bars, the specific shielding effectiveness, and this specific shielding effectiveness was determined by dividing the shielding effectiveness by the density and multiplying it by the thickness. And the other figure of merit was the surface conductivity. As can be seen, both G-Shield products have good specific shielding effectiveness. And as expected, the one with the carbon black does not have a good performance. But I would say that the biggest outlier is the material from competitor one, the ABS stainless steel fibers, as the reported conductivity does not match the shielding effectiveness. So it seems awkward to have such small conductivity and simultaneously have so much good shielding effectiveness. So for us, this was kind of tricky. Transitioning now to ExiShield. So this product offers unique features and serve different application requirements, from electrical conductivity to adhesion properties. And that's why we have these two versions, the water-based and the solvent-based. As you can see, they have different weight loss, different solid content, different viscosities, and at the end, different benefits. But let's now dive into the electrical features in detail. So on this slide, I'm plotting the shielding effectiveness of the two versions, water-based and solvent-based, as function of the thickness. And in red, we can also see the surface conductivity of both products. What is immediately possible to observe is that the surface conductivity of the water-based is 1 order of magnitude higher. So we have 3,000 Siemens per meter for the water-based, while for the solvent-based is in the hundreds orders of magnitude. And because of that, its shielding performance is also better, the one from the water-based. So we are talking about an average of 13 decibels of difference, regardless the thickness. Well, the great advantage of the solvent-based solution is the fact that it allows to produce thick coatings with around 300 micrometers. And not only that, because you will see that the solvent-based also has an opportunity when we were on the need of having more absorption than reflection. And that's this, the next slide is about it. So if we take into in consideration a thickness of 75 micrometers, as we can see, the water-based provides 28 decibels of attenuation, shielding, while the solvent-based only 13 decibels. However, when we look at the shielding mechanisms behind these numbers, we can see that the solvent-based has a bigger contribution of absorption, which again might be important for certain applications. So at the end, solvent-based ExiShield absorbs more, but has lower performance at this thickness. So if you want to, if you want to make it work better, you need to increase the thickness. Maybe just have a sip of water. The water-based ExaShield was tested in a real-world application. In this case, we made some tests with electronic enclosures. We took a polycarbonate ABS inverter box from an electrical vehicle, an automotive inverter, as can be seen on the image at the left of the slide. And we tested two different scenarios to measure the shielding performance using the equipment that you saw on the previous slides. So we spray coat the box only inside, and we also spray coat the box inside and outside. In both cases, the coatings have roughly 30 to 40 micrometers thick. As you can see on this plot, I'm also showing the shielding effectiveness and the two contributions of absorption and reflection for the two scenarios, so coated inside only and coated inside and outside. And basically, to perform the shielding tests, we use the lid of the box, and we put the lid of the box in between the waveguide. So that was how we measure these numbers. As can be seen, by coating only inside, we were able to attain 31 decibels of attenuation, total attenuation, and this value increases up to 45 dBs when both sides were painted. And actually, what was interesting to saw was the fact that the reflection mechanism decreased a little bit and the absorption increased a little bit as well. But we went a little bit further and we decided to make more comprehensive tests. Actually, we call it EMC tests between commas. Let's call it like this. And the purpose was to validate the effectiveness of these shielding solutions in practical environments. We cannot call them real EMC tests because they were not performed inside an isolated and coiled chamber. But despite that, they were very good to understand what is happening. Because they allow us to simulate electronics emitting signals in the interior of the box, such like an inverter would work. So to perform those tests, we use a pocket-size comb generator, and this equipment typically emits periodic signals with a base frequency of 100 megahertz. And this was our device on the test, as you can see on the figure on the left. And this equipment was put inside the inverter box, which is our shielding enclosure. Those two were then put apart by 1 meter from an antenna that is connected to a spectral analyzer. As you can see on the image, we decided to close some gaps and holes of the box with aluminum foil to make sure that no signal came off out of there. Okay. So we always start this test by collecting the background signals. So in this case, the comb generator is completely shut off, so without emitting any signal. So we just have the spectral analyzer collecting again the background measurements. As you can see on the green plot, we could saw some radio, some 4G networks. So again, this happens because we were not making measurements in a properly isolated uncoiled chamber. So any kind of signal was observed by the spectral analyzer. Then we turned on the generator, the comb generator, and as you can see, we saw the periodic signals distanced by 100 megahertz between a frequency range of 100 megahertz and 4.5 gigahertz. The reference spectrum that you are seeing here is the one that already has the background signals subtracted. Okay. But the real test was then made to 3 different enclosures. On gray, you can see the measurement made with the inverter box completely neat, so no coating, only the PC ABS. On red, you have the red spectrum is the one from the inverter box painted only inside, and the blue one, the inverter box painted inside and outside. In all of them, we can see the periodic signals from 100 megahertz to 4.5 gigahertz. And again, please bear in mind that these spectra were normalized, and we have to subtract the background signal for the sake of easiness, and to take into consideration all the noise coming from other networks. But despite that, what we could immediately observe was a significant reduction in the receive the signal using our water-based ExaShield. And this becomes more prominent in the box that was coated inside and outside, so the blue spectrum. So as you can see, the peaks are much more smaller. This seems to be true in the entire range of frequencies, but somehow we need to clarify mostly for low frequencies. We are afraid that for low frequencies, we need to understand what is really happening at this application scenario. And that's it. I think the take-home message is the one that I have written here. So Graphenest represents a paradigm shift in EMI protection, offering unmatched performance, versatility, and reliability. I would like to thank my R&D engineers, and thank you for your attention. I'm ready to take your questions.
Excellent, Bruno. Well, thank you for that. That was a great presentation, and it's good to see so much data to represent, what you guys have done and the amount of testing that you do. I have a couple of questions for you. We have a few from the audience, so if anybody else who's watching the presentation has some specific questions, please go ahead and present them. So, it was interesting to note the difference in performance at the different frequency levels. I have just some questions about adoption from the commercial side for this particular product. Who are you targeting? I mean, if we look at like OEMs, like for the automotive sector and such, they have a whole supply chain, and they're going to purchase in their cabling, or they're going to do the supply somewhere in the supply chain is where the EMI shielding comes in. Where within that ecosystem are you guys targeting for your product?
There's no straightforward answer to that. What I can tell is, for instance, for the PVC, it was pretty easy, because when we partnered and we did a joint development agreement with Delta Technique, we were already knocking on some doors that were open to them since the beginning. So they had their clients on power and data cables, and we were trying to convince those to make something with us, but they were already in contact. So it was easy going there together with Delta Technique and convince them to do something with us. So I would say, yeah, tier two, it's going to be our, even tier one, it really depends. But for cabling, tier two, you need the cable manufacturers then to provide those cabling to other kind of companies like Aptiv, Bosch, which will be the tier one, right? And then the OEMs. But it really depends. Sometimes we try to close the loop, the entire loop. So sometimes we try to convince the OEMs to have a look at us, and they go down on the supply chain. So they contact the tier one, and the tier one contact the tier two until they get to us. So there's no straightforward. Each case is a case.
And what kind of reaction are you getting when you're introducing this product? Because the benefits seem pretty obvious with lightweighting, lower cost. Are there resistance because it's simply a new material? They don't understand graphene, or what kind of hoops do you think you have to go through to get to the commercial adoption now?
For this kind of application, and this is something we are now using to say here at Graphenest, we are fighting against traditional ways of doing stuff. So that you can imagine the typical reaction you get when you are trying to fight traditional ways of doing stuff. Sometimes you are also fighting against standards. For instance, on cabling industry, certain standards demand that an amount of metal braiding should be existent on the cable. So it again, people are curious. They want to know more. They want to test. We need to define sometimes the best design to do it. But at the end, again, is fighting against traditional ways of doing stuff.
Yeah, I think that's true for the entire range of applications for graphene. One of the questions from the audience is about the durability of the coating. So if I understand correctly, like you had the enclosure, the electronics enclosure, where you could simply spray apply the coating to that. Have you done any tests how durable the adherence is, or resistance to braiding and friction?
No, not yet. We have now trying to implement some test measurements like scratch and those kind of crosscut. We have that now here at our lab, but we are on the early days of those. So, but for the impression that we have applying the coating, doesn't seem that we're going to have any problem related to that.
Okay.
And really depends on the substrate somehow. We have been applying it in different substrates like polycarbonate, Kapton films, PVC as well, sheets, PET, PEN. And at the end, you need to play as well with the surface tension of those substrates to make sure that you have the best application, the best thickness, homogeneity, and so on. It's again, this is not a product that fits all the applications, and there are some fine tuning to be made in each case.
Of course, and again, if I understand correctly, so you have the ability to do this as a spray application, but with some of the polypropylene or the PA6 product, do I understand correctly? Is that where the graphene is embedded in the material, or is it?
Yes.
Okay.
So two different product lines. One is compounding, other one is coatings. So compounding is all the polymers, polar and non-polar. So right now we have PVC and PP ready to be commercialized, and we are trying to develop and finding partners in some cases for other polymers, PVT, PA6, polycarbonate. And in that case, it's compounding. So we rely on the partners through joint development agreements to compound, and they rely on us to guide them through the formulation with the shielding measurements that we can do here at Graphenest. So we do all the shielding and conductivity measurements here. We can also look at how good the dispersion is on the polymer, on the compound, and so on. And through that, we guide the formulation. We can tell them, okay, it's not conductive enough, so the shielding is not good, or it's too much conductive. Price-wise, this is going to be expensive, so reduce the filler content to make it more appealing to the market. So we guide them through the formulation, but we need them to make the compound. On the coating side, that's not the case. So on the coating side, we are completely autonomous. So we do the formulations here, and we make all the measurements here. So this is up to us here at Graphenest.
So on the compounding side, that would the partnership with Hubron would be an example of the compounding, I assume.
Yes. Yes.
And Hubron, by the way,
and they serve different purposes actually. So PVC was made for cabling industry, while the polypropylene was made for electronic enclosures. So that's why one is for extrusion and another one is for injection molding. So completely different purpose, different worlds. They overlap in terms of features, but they serve different markets at the end.
Excellent. And there's some general questions. I don't know how much of this you might be able to answer or how much of it is trade secret, but there was a question about, like what method are you using to produce your own graphene, and what kind of load factors do you find you need to hit in order to get to the
so yeah, at Graphenest we use liquid phase exfoliation, so we have a patent on it. If someone is curious about it, you can just Google patent and check the patent. So liquid phase exfoliation, ultrasonic cavitation, ice shear mixing, so those kind of things. But what is special about us is our yield and the design of the device that was built to make it to have that yield at the end. In terms of filler content, this is a kind of proprietary information, but what I can say is it's not small and it's not big. It's something intermediate.
Yeah. Okay. Are you actually making any of the graphene you produce available to anyone else, or is it all for your internal use?
No. We also make it available. Apart from the graphene that we produce and we use for shielding products, we also have the graphene powder. But typically, to supply that, it has to be strategical. We don't want to supply just for the matter or for the sake of supplying it. We want to make sure that it serves a purpose and is well aligned with our objectives.
Understood. Now that makes perfect sense.
And this is even more important when you have now developments undergoing, and when we have now products being produced with our graphene, and we need to make sure that we have stock to fulfill the necessary quantities to produce products. So without knowing where it's going to be used, we're not going to release any material.
Understood. There is a question about the availability of the product in different markets, in particular for the U.S. You're based in Portugal. We know that with the REACH consortia, there's agreement or permission for graphene to be distributed in the EU pretty widely, and in the U.S. you have EPA and TSCA requirements. Which geographic markets are you targeting, and what's on the horizon?
We want to have a global presence. So we sent material everywhere in the world. So we already sent to the United States, Singapore, China, Australia, New Zealand. So we did it in the past. We can do it. And right now we can do it because we have a small scale production. So we are below the 1 ton, which is the maximum amount authorized by the REACH. Without having the REACH, that's it. So we can supply it everywhere in the world. But we are in the process of scaling up our capacity, and we're going to comply with REACH in the near future, and then will be even easier to send it all over the world.
A couple of other questions here. One, have you ever applied this kind of a coating to a textile?
Yes, but textiles have other issues, which is flexibility, stretchability, and so on, and those kind of things impact the results. And it really depends as well. For instance, ExaShield is not proper to be used on textiles. Textiles typically demand like polyurethane coatings, those kind of binders that will work better on TPUs as well, thermoplastic urethanes. But we don't have any formulation specifically for textiles. But this is something we can discuss if someone has an interest.
Of course, yeah, that was just one of the questions that we had. Somewhat related to this, so especially in the compounded solutions rather than the spray, when you're compounding this into a polymer, have you tested what the effect is on the mechanical properties?
Yes and no. So we know that the material becomes a little bit brittle, but the impact is small. So we have some data, but is neglectable data. So the material does not change as much. And again, it has to do with the loading level of filler. So we are not putting a lot. So it's an intermediate value. So the effect at the end on the mechanical properties is not bad.
Excellent. You mentioned a couple of the advantages, for example, light weighting and also lower cost. And I want to ask a question. I hope I can make sense with this. One of the things to consider is in processing. And you made a comment that had really caught my attention, in that the throughput for a cable manufacturer was much higher if you could replace some of the braiding.
Yes.
So I want to ask a combined question, and so sorry if this is confusing, but talk about if a cable manufacturer wants to use this product, do they need to have an additional process step or a different process step or special equipment? And then talk about, the cost benefit. Is it just on the cabling part of it where they're saving money, or where else is there an advantage? And how much of an advantage do you think the manufacturers are going to get?
No, well, for the cabling industry, it's easy to answer. So the braiding is very slow, like I said. So typically dozens or even hundreds of meters per hour while on the braiding process. But if you replace part of that braiding by an extrusion process, a typical extrusion process where you are extruding the cable like you do for insulating the cable, you are on the thousands meters per hour. So you have this up to 40 times bigger throughput. If we think on the same kind of thought for the electronic enclosures, is the same. So instead of having a metallic enclosure that passes through several and consecutive steps until get this final shape, so you need to mine the metal, you need to make the ingot, then you need to somehow make the conformal shape of the electronic enclosure. If you have a mold and the polymer, right, it's just a matter of inject the right shape or the right design. So you also have some savings in that sense with less processing until you get the shape you want. So I think I don't know if I answer your question, but
yeah, no, that makes sense. We did study, as the Graphene Council, we did a study of graphene for EMI shielding some time ago, and one of the things that we found in the end user side of it was the curing rate. Like, how long does it take for the coating to cure? I think you mentioned a 2-hour period for the water-based.
yes.
Did I get that correct? And how does that compare then to maybe some traditional coatings in terms of the cure rate? Is that equal to, faster than, slower than?
You have faster ones and slower ones. So, and this applies for the water-based. The solvent-based is much fast to cure because it's solvent. So you have lower boiling points, and you can cure it faster. But it's something in the middle.
Well, maybe just to ask a couple of last questions. If you look at the EMI shielding enclosures, that's one market that lends itself to the coating, the spray coating application. And then you have the cabling market, which is more for the compounded material, I assume. Do you have a sense which of those markets is probably the most achievable for you in the near term? Which is easier to attack?
Right now, I think it's the compounding. It's more well established, but price-wise, the coating will be better. People tend to pay more for the carbon or graphene-based coatings, so they are very expensive. You can buy small quantities at high prices. So to earn money, will be better to be on the coatings. But I think the compounding is more interesting, and there are much more opportunities at the end.
Excellent. Well, I appreciate you sharing this information with us. I want to congratulate you on the progress that you've made, and I also appreciate the amount of data that you're sharing to, prove the case of what you've developed. Any last closing comments you would like to make, Bruno?
No, just to say that I was glad to be here. People, I think, will have my contact. So if anyone has an interest or hold an interest on what we have been doing here at Graphenest, or want to specifically chat about any topic that they saw today, I will gladly welcome those. So thank you, everyone.
Excellent. Well, thank you again, and thank you for participating with the Graphene Council. We appreciate you as a member, and for everybody watching, again, thank you for your interest and attention, again, for this exciting material that we see making its way into real-world applications and products. Have a great day.
For more information and to connect with expert partners, contact the Graphene Council at thegaphenecouncil.org.